Hello, this is a short video to explain how we can answer a problem or solve a problem about chi-squares. So the main concept we are discussing now is the chi-square calculations. When you do an experiment, when you carry out an experiment, you obtain results. These results are called the experimental results. And these experimental results require your observation. You have to look at the phenotypes, you have to calculate the ratios of phenotypes, and these are what we call the observed results. For example, when Mendel discovered that 100% of the flowers were red in the first generation, this is an observed experimental result. But now that we know a lot about alleles and about the crossings, we can expect the results. So we do Punnett squares, we draw Punnett squares, or we draw genetic diagrams, and the purpose of these Punnett squares or the purpose of these genetic diagrams is to try to anticipate or know the probability of the results. These results are not experimental. These results are theoretical results, and these results are called expected results. Why? Because we are expecting the probability to be as we obtained from the Punnett square and the genetic diagram. Of course, the experimental results are on Earth. And when you get the experimental results, you want or you are expecting your experimental results to be, or your observed results to be very close to the expected results. Usually this is not the case. There are differences between the expected theoretical results obtained from the Punnett squares and the genetic diagrams and the observed results obtained from the experiment. So there are always differences, but the differences might be minor differences, or scientifically speaking, we can say that they are insignificant differences. For example, because you didn't use a large sample, you used a small sample, and you know that the smaller the sample, the smaller the probability that the expected results are similar to the observed results. So it might be due to a small sample. Most of the time when you work on a small sample, there are differences between the expected and the observed results, but the differences are minor. But sometimes the differences are major. And of course, this raises the doubt that there is something wrong. So if the differences are significant, then there is a great doubt or suspicion that there is something wrong. What could be wrong? For example, you have postulated a wrong hypothesis. Your hypothesis might be incorrect, or you might have errors in your procedure, or the hypothesis might be correct, the procedure might be correct, but there has been something that disrupted your expectations, and that thing is crossing over, that broke down the complete linkage and converted it into incomplete linkage. Because when you're expecting the ratio to be 1 to 1 to 1 to 1 in a dihybrid test cross with free genes, or 1 to 1 in a dihybrid test cross with complete linkage, and then you find that it is neither 1 to 1 to 1 to 1 nor 1 to 1, despite your correct hypothesis and your correct procedure, then there must have been some sort of crossing over that changed the ratio to parental 1, recombinant 1, recombinant 2, parental 2. who will decide, or what exactly will decide whether the change is or the difference between the expected and observed results is significant or insignificant? It is the chi-square value, and it makes sense because the chi-square value, which we denote x square, equals the sum of this symbol is sigma, and it indicates the sum of what? Of the observed results minus the expected results squared divided by the expected results. So first of all, why do we square in the formula? We square because we don't want this value to be negative. We want it to be a positive value, to be an absolute value. So if the expected number of organisms is smaller, that's okay. But if the expected number is bigger, then the numerator will be negative. So in order to get the absolute value, the positive value, we square. And that doesn't make any difference because we are talking about the squared difference. And why are we dividing by the expected value? Because you might have a big value here in the numerator, but the expected value is essentially big. So a big numerator over a big denominator will result in a small x value, so the difference wouldn't be big. So it's not enough to find out that the difference between the two is big, but how big is it related to the original value, as you know. And why is there this symbol sigma? Because we are doing this for every trait, and then we are summing up all the chi-squares for all the traits, as we will see in the example. Of course, we will be using this formula of the chi-square. So the chi-square is actually nothing but the squared value of the sums of the differences between the observed and expected results over the expected results. Here we have a test cross between a hybrid dominant individual that is red flowered. So the individual genotype is R capital, R small, and this is a monohybrid test cross, of course, because it will be crossed with a recessive white flowered individual. This is what we know as, without mentioning it in the problem, this is a monohybrid, not a monohybrid cross, but a monohybrid test cross. And we know beforehand that the ratio should be 1:1 because this individual, R capital, R small, gives two types of gametes, R capital, R small. The other individual gives one type of gamete. So the genotypes of the offspring would be R capital, R small, to R small, or 1:1. So the expected theoretical ratio from the genetic diagram is 1:1. But there remains one important step, which is to translate this, or to transform this genetic ratio 1:1 into a number, into a numerical value. So here we have, here it should be red, not purple. So we have the number of red flowered plants is 329, and the number of white flowered plants is 299. So first of all, we should calculate the total number of offspring. The total number of offspring is 329 plus 299. In such a case, the sum would be 9 and 9, this makes 18, 3 and 9, this makes 12, and then it is 628. This is the total number of plants that we obtained in the first filial generation. So according to our Punnett square, or according to here, we didn't do a Punnett square, we didn't draw a Punnett square, we drew a genetic diagram. The ratio should be 1:1. So the total parts are 2, and therefore we are expecting this genotype to be represented by half those offspring, which is 314, and the other genotype to be represented by 314, because theoretically the ratio should be exactly 1:1. And since the total number of obtained offspring from the experiment was 628, then the R capital, R small individual, or actually the red-flowered individual would be 314, because in chi-squares we are mainly concerned with the phenotypes, not with the genotypes. So if we are concerned with the phenotypes, why then are we writing the genotypes? Because we just want to know the ratio between them. But actually what happened is that we did not obtain 314 red flowers and 314 white flowers, but we obtained 329 red-flowered plants and 299 white-flowered plants, which means that the number of red-flowered plants was bigger than expected, whereas the number of white-flowered plants was smaller than expected. So these two numbers and the ratio between them, which are the observed values and the observed ratio, are not consistent with the expected ratio. So we are going to calculate the x-square value or the chi-square value according to the formula. So as I said, the expected ratio is 1 R capital, this is R capital, R small, to 1 R small, R small. As I said, what matters is the number of the phenotypes, not the genotypes. We write the genotypes only to get the ratio. So we are expecting the ratio to be 1 red-flowered to 1 white-flowered, or 50-50, which means 314 red-flowered to 314 white-flowered, which is not the case. So the expected, this is a very organized way of answering problems on Punnett squares. So you write the phenotypes above, because this helps you know that you have two different phenotypes. And why is it important to know that we have two different phenotypes? Because we will need to calculate what we call the degree of freedom. And the degree of freedom equals what? It equals the number of phenotypes minus 1. The number of phenotypes minus 1. So in such a case, the degree of freedom would be, we have two different phenotypes, so it would be 2 minus 1. So the degree of freedom equals 1. Why am I calculating the degree of freedom? We will know very soon. So we write the phenotypes and we deduce that we have two different phenotypes, and from this we calculate the degree of freedom. These are the expected numbers that we were expecting from the Punnett square or the genetic diagram. But on Earth, when we carried out the experiment, we found out that the red were 329, more than 314, and the white were 299. Of course, if the red are more than 50%, then the white will be less than the 50%. So we will calculate the difference, because there is a difference between what we observed on Earth from the experiment and what we were expecting. 329 minus 314, this is 15. And the difference here is again 15, but minus 15. So as I said before, since the observed in the red was 15, was greater by 15, then definitely the observed number of the white will be less by 15. And that's why we square, because we want to get positive values. So observed minus, and that's why it doesn't matter whether you write expected first or observed first. It doesn't matter, because at the end of the day, you will square the value, and the square of the value for red is 225, and for the white is 225. But in the formula, we have in the numerator observed minus expected square divided by expected. So 225 divided by the total, 314, and here 225 divided by the total, 314. And of course, the denominator will be common for both. When you add this value, which is O minus E squared for the first characteristic red, and to this value, which is the same value for white, and then you divide by E. Why are we adding? Because we have here sigma. So x squared, or the square of the difference, is the difference squared divided by a common denominator, and you get your chi-square value. It is this chi-square value that will indicate you whether the difference is significant or not. But you cannot do this on your own. You have to make use of the tables that would help you. I'll go backward to find out the table. The table is there. So we obtained a chi-square value that is 1.433. And these are the tables that help us to know or help us know whether the difference is significant or not. Of course, this x squared value is derived from what? It is derived independently of this sign. It is derived from the difference between the observed and the expected. So it is an indication of the difference. If the difference is big, then the square will be big. If the difference is small, then the square will be small. The x squared value for this experiment was 1.433. I have to locate it in the table to know whether it is a significant difference or an insignificant difference. But first of all, I have to know that I have columns, as you can see, and rows. First of all, I have to decide which row I will look for the difference, or I will locate the difference in. So we said that we have two phenotypes and that the degree of freedom equals the number of phenotypes minus 1, which means 2 minus 1, which means 1. So I'll be working in this row, Where can I locate the calculated chi-square value? It should be located here between 0.45 and 2.7. Why? Because 1.4 is bigger than 0.4 and smaller than 2.7. So it is located here, which means that the value is insignificant, or the difference is insignificant. And if the difference is insignificant, then it's most probably due to a small sample, most probably due to a small sample and not due to an error. But if my calculated x squared had been 6.6, for example, then it would be a significant difference. And in such a case, I would say that it is a big difference and that most probably I have an error in the hypothesis or in the experimental procedure, or maybe because there was crossing over. Why is here we have the demarcation line at probability 0.05. What does this mean? Probability 0.05 means a probability 5%. Here the probability is 10%. Here 0.5 means the probability is 50%. So as we go to the left, the probability increases. The probability increases that what? That the difference is only due to chance, or that the difference is only due to a small sample. So the smaller your x squared value, the more it would be located in the table to the left, and the more this indicates that your difference is insignificant and that it's only by chance. But greater than, if your value, your difference was big, this means, for example, here, that your probability is 1%. 1% is bigger than 0.5%. Here, this is, sorry, it's smaller. Here we have 5% and here we have 1%. So as we go to the right, the probability diminishes because here this is 2%, here this is 1%, here this is 1 per 1,000. So the probability diminishes. Which probability diminishes? The probability that it is merely due to chance or due to a small sample. So if it's not due to chance or due to a small sample, then it is due to error. Of course, if my x-squared value falls below probability 0.05, then my experiment is okay. Then I will accept, or let's say fail to reject, because as I said before, we cannot accept absolutely, we cannot prove with certainty, but fail to reject the null hypothesis. What do we mean by the null hypothesis? We mean the null hypothesis postulates or assumes that there is no difference between the expected and the observed results. Of course, when my difference is very small, then I can accept the null hypothesis, or more correctly speaking, fail to reject the null hypothesis. But if my difference is big, then I cannot accept the null hypothesis that says that there is no difference between the observed and the expected, and I would reject the null hypothesis and repeat the experiment, maybe with a new hypothesis or maybe with a new experimental procedure. The last thing to say is what we call the critical value. We said that in this experiment, we would be working on degree of freedom 1 because we had only 2 phenotypes. But if we had 4 phenotypes, we would say 4 minus 1 equals 3. We would be working here. But in a particular row, like this row, this is the critical value. So in our previous solution or example, when our chi-square value was equal to 1.433, we said that we failed to reject the null hypothesis, which means that we accepted the null hypothesis because our difference is smaller than the critical value. So what is the critical value? The critical value is an x-squared value because all the values in this table are chi-squared values that are put in the table to guide you. So the x, like in the statistical tables, for example, or statistics tables. So what is the critical value? The critical value is an x-squared value that corresponds to probability 0.05. What is probability 0.05? It is the maximum possible probability that our difference is only due to chance and not due to an error, because we said that the probability here is we have here 5.5, which is 50%, and then we have 10%, and then we have 5%. After this, the probabilities are smaller. So to the right of 5% or probability 0.05, the probability diminishes that it is due to chance. And since the probability diminishes that it's due to chance, then it is due to error. So the critical value is an x-squared value that corresponds to the probability level 5%, but I have to complete and say at degree of freedom 1. Whereas, for example, 7.8 is the critical value, again, because it corresponds to probability 0.05, but this time at degree of freedom 3. 11 is the x squared value, the critical value, because it is the x squared value that corresponds to probability 5%, but this time at degree of freedom 5 if I have 6 different phenotypes. So 0.05 or 5%, the probability equal to 5% is a critical probability because it corresponds to a critical value at a certain degree of freedom. I need to correct something I said during the presentation that 0.5 means what? 0.5 means that there is a 50% probability that this is due to chance and not due to error. But 0.5 means only 5% and 0.01 means only 1%. So less than 5%, this cannot be due to chance. So compared to the values to the right, the 5% is the biggest, but compared to the values to the right, the 5% is the smallest. So there can't be a smaller probability than 5% that indicates that it is due to chance. Thank you.